Okay, let's start the second part, Gaurav. Okay.
Yeah, okay.
Okay. So, uh, okay. If you are here, people of CAS, what did we do? We, in the first part, have done or have studied the mechanism of nucleophilic substitution reaction in haloarenes in presence of electron withdrawing groups at two positions, one at para, how does it affect? And we've also looked at the mechanism of NSR of haloarenes in presence of, again, electron withdrawing groups at ortho. We've seen these two positions. Now we'll look at the third position, which is the meta position, and then we will form an important opinion as to why NSR is easier in case of ortho and para electron withdrawing groups and not in case of meta electron withdrawing groups. Okay, shall we continue, Gaurav?
Sure.
Okay, so let's do the exact same drill that we did before. We'll again start with, I'll change the color because I don't feel like doing that. Okay, so here we'll take again chlorobenzene, and benzene would have three bonds. Chlorine has three lone pairs of electrons. Now the nitro group would be at meta position, which is here, right? And with this, we have the nucleophile OH minus, and we are about to see the nucleophilic substitution reaction in case of nitro group at meta position. So again, very similar to the para and the ortho mechanisms, OH minus actually attacks the carbon, which already is hosting the chloride group. And this reaction or this particular step is a slow step, takes place slowly. And what do you see as a result of this? What happens here is, we've done this before also, this double bond can no longer be there. It forms a negative charge on the adjoining carbon, and you get your first resonating structure. You can hear me loud and clear, Gaurav?
Loud and clear.
Great. Here we have one bond to OH, simultaneously another bond to chlorine. This double bond, which got broken off because of tetravalency, now is a negative charge on this carbon. Yes. And the bonds which were there earlier just stay as it is, and we write NO2 at meta position. This is resonating structure number one. What happens after this is we again move electrons. The negative charge becomes a new bond. And once you have a new bond here, this bond cannot coexist. It has to become a negative charge on the next adjoining carbon. Right, Gaurav? Following
Yes.
along? Okay.
Yes.
And now our resonating structures start. We have the next resonating structure looking something like this: OH here, Cl over here, a new double bond here, and this is a negative charge at this para position, and this bond was there before, and you have NO2 group as it is at meta position. Now, this is resonating structure 2. Then after this, we move the negative charge again to this position. This double bond cannot coexist together, so it moves and becomes a negative charge on the adjoining carbon atom, right? And then we can see the next resonating structure as a result would look something like this. Again, OH, Cl together. This double bond was there before. This is a newly formed double bond. This is a newly formed negative charge because we moved it here. And NO2 group was at meta position, resonating structure number 3. All good? You're following, Gaurav?
Yes.
Okay. What is going to happen next, guys? What happens next? Again, negative charge becomes a bond here, and chloride gets thrown away, and nucleophilic substitution is complete. This is a fast step. And so the last structure that you will have here, the final structure product that we have here is, this is a new bond which is formed. These were there before, NO2 here at meta. Here now we have OH because Cl minus as left as your leaving group. Okay, this is the entire reaction. Gaurav and
Okay.
people watching the video, what is the essential difference between when we see resonating structures at meta and when we did resonating structures before at para position and at ortho position of nitro groups? Do you find any difference whatsoever, Gaurav?
Here, nitro group does not come into resonance, so it does
Great.
not
See,
uh,
hmm.
take away the electron density towards itself.
Mm-hmm. See, really great point, Gaurav. I'm actually glad you got it. So here in ortho and para, what do we see? The nitro group takes away the negative charge which came on this particular carbon. I've started here. This carbon got the negative charge because of OH entering into resonance with benzene, and the nitro group was effectively able to take away that negative charge, although momentarily, but it did take away the electron density from the starred carbon over here at this position. This was for ortho structure. Similarly, if you look at para structure, here at this resonating structure at this position, there is a negative charge on the carbon, which hosts or which contains the nitro group. Nitro group enters into resonance, takes away that electron density, and then we move forward with the resonating structures. But if you look, an essential point of difference when you look at meta resonating structures, when you have nitro hosted at the meta position, do you find any point where that electron density is taken away by the NO2? This is where electron density was at ortho, nitro was at meta. This is where electron density was at para, nitro was at meta. And this is where electron density again was at ortho. So we had electron density coming, the negative charge coming to two ortho positions and one para position. Whereas the nitro, the electron withdrawing group, its one job was to withdraw that electron density, but it's at meta. It's not really withdrawing that electron density or the negative charge from the carbanion, which is formed on benzene, which is why it has no role in affecting whether the chlorobenzene or the haloarine is undergoing nucleophilic substitution or not, which helps um, haloarine to undergo nucleophilic substitution, electron withdrawing only at ortho and para. And this is the reason why. I hope it is very clear now. Please let me know if it is clear. Okay. And one more thing, once you're here on the part 2 of this video, this is a question that I have put up on your screen. Take a screenshot, take a moment to read the question. This, let me tell you something, this is a multiple correct answer type question. That means multiple of the options A, B, C, D, all four could be correct. Some three could be correct, some two could be correct, or just one could be correct. All possibilities are open for this question. Let me know. If possible, I'll put up a poll on WhatsApp group. Let me know which all options do you think are correct. You can select more than one option in the poll. You can do that. If it's feasible, I'll put up a poll. Otherwise, keep it in your mind. I'll ask this question in the next class whenever you do show up. Okay. With that being said, I'll just move to a little bit more portion of this, and then maybe we can consider this part over. Okay, Gaurav, ready to move to the next thing?
Ready.
Okay, what I want you to do, Gaurav, is look at these two lines that are there on your screen. I'll just take it up a little further so it's very much visible to you. Can you see this clearly? I'll
Yes.
number this 1 and 2. There are 2 points written in red ink, point 1 and point 2. Read these 2 points out and tell me what I fill up in these blanks here. Take some time, read the points out, Gaurav, and I actually want you to answer me what I should fill up on the places here. And do the same, you guys as well. Whenever you're ready to answer, Gaurav, let me know.
Okay. So for first question,
Mm-hmm.
It will be ortho and para positions.
Okay, what is the first question asking us? It's asking us if electron withdrawing groups are there at what all positions, then they can withdraw the electron density from the carbanion. That just means carbon with negative charge on the benzene ring. We saw
Hmm.
which positions can withdraw those effectively, and thus, as a result, they stabilize it. So the answer, we've already seen this, is what all positions? We have ortho and para
Para.
positions. They effectively withdraw the negative charge which is there on the carbanion, right?
Yes.
Okay. And what the next question asks us is electron withdrawing groups, when they're present at what position, does not in fact withdraw the electron density from the carbanion and thus has no role whatsoever in the reactivity of haloarenes towards nucleophilic substitution. And what do we get? There is just one other position left,
Meta.
which is great, meta position. We've got this covered.
Yes.
Okay, great. I'll go into a little bit of electrophilic substitution reaction, guys, so that when we meet up the next time, it's a bit easier on us to understand what actually is going on. So what I'll do is I'll just scroll down a little bit and I'll talk about what electrophilic substitution is, and then maybe we can do it together. Or better what, let's just continue this line of topic as it is. Okay, Gaurav, we are talking about something called electrophilic substitution reaction. It is also there for 12th graders now and CBSE. Okay, so what is electrophilic substitution reaction? Now, NSR was nucleophilic substitution. There, a nucleophile with a negative charge substituted another nucleophile with a negative charge. In electrophilic substitution, what do you think happens? Electrophile. Electrophiles would have positive or negative charge, Gaurav. What do you think?
Positive charge.
Mhm. E plus replaces another possible electrophile, which would be there in the molecule, and that's why these are called substitution, replacing one electrophile with another electrophile. Now, why does electrophilic substitution take place in haloarenes? We are in the chapter of haloalkanes and haloarenes. That's because arenes, aromaticity comes from benzene, and benzene rings are electron rich in nature. They have three double bonds. They have a lot of electron cloud around that ring, which can act like a good source of electrons where these electrophiles can get attached to, because electrophiles are in essence positively charged. Electrophile means electron seeking. They're looking for electrons. They're looking for negative charges, right? Gaurav, you're following this?
Yes.
Okay. And some of the electrophilic substitution reactions we are going to look at are these ones: halogenation, nitration, sulfonation, and FC. FC stands for Friedel-Crafts. There are two Friedel-Crafts reactions. One is Friedel-Crafts alkylation, and the other one is Friedel-Crafts acylation. These are the two reactions we are going to look at. Now, once we talk about electrophilic substitution, when we talk about haloarenes, for example, chlorobenzene is the one example we're going to stick to here. Chlorobenzene electrophile, chlorine is not an electrophile on chlorobenzene. The chlorine is not going to get replaced in electrophilic substitution. The chlorine is going to stay there in electrophilic substitution. Something else gets replaced, and that is hydrogens that are there on the benzene ring. So chlorobenzene, if you write it out formula wise, is C6H5 bonded to Cl, right? Gaurav, do you agree with me
Yes.
on this? There are
Yes.
5 hydrogens on each of the carbon on benzene, from which one or two hydrogen, essentially one hydrogen, because we're looking at one round of electrophilic substitution, one hydrogen gets removed and an electrophile gets attached in that position. So hydrogens getting substituted by another electrophile is electrophilic substitution reaction at its core. We've got this.
Yes.
Okay, so electrophilic substitution happens at what place, what positions in haloarenes? It again takes place at ortho and para positions, because haloarenes are ortho-para directing groups. These are ortho and para directing groups. Why are they ortho and para? If you look at resonating structures, which we did in class, but still, if you look at resonating structures of chlorobenzene, here there is a negative charge because the bond moved here. There are two bonds which were there earlier. Now let's move these bonds. Just one second. Yes. So this bond, negative charge will move here, become a bond. This bond moves to the next carbon, becomes a negative charge. So this is how this looks for the third resonating structure. Then this negative charge becomes a new bond. The bond becomes a negative charge. And this is how it looks for the fourth resonating structure. And the last resonating structure, this becomes a new, sorry, oh, okay. And at because this lone pair of electron, it moved here, right, onto the benzene ring. Chlorine has a double bonded structure. We've done that partial double bond nature of chlorine. And then, oh, sorry. And it will have a positive charge because one lone pair is already inside in conjugation with the benzene ring. So this has a positive charge, double bond and a positive charge. And what happens in the last step? This negative charge becomes a new bond, new double bond, and this double bond on chlorine goes back up to chlorine, and chlorine gets its three lone pairs back again. Here you have the new bond, and these were the two earlier bonds. Now we have five resonating structures of chlorobenzene. Gaurav, you're there with us? You
Yes.
following?
Yes.
Okay. Now, what do you see? Where are the negative charges centered? Where are the negative charges present? This position, again, what is
Ortho
this
and para.
position, Gaurav? Yes, this is ortho. And again, where else do you have this position? This is what position? This is
Para.
a para position. Great. And you have at this position, this is
Ortho.
an ortho position. So two ortho and one para position. So where are the electrophiles with positive charges going to get attached to ortho and para? Because there you have the maximum electron density in case of haloarenes, or particular example if we speak of, it's a chlorobenzene. We've got this?
Yes.
Okay. I hope CAS people, you've also got this. Now, when we've already established that which isomer will be the major product. So in case of electrophilic substitution reaction, we have two places, one ortho place and one para position. So you'll have products which will be mixture of ortho substituent and para substituted electrophilic substituted products. Which becomes the major product? One becomes the major product, one becomes the minor product, meaning one is produced in more quantity and the other is produced in less quantity. Usually, para isomers you will see are the major products. Why is that? Because para isomers are usually the major product. If you look at the blank space here, what do we fill here? That's because orthoisomers face a great deal of, or experience a great deal of what? Do you have a clue, by the way, Gaurav, to this space? Gaurav, are we connected? Are you there with us?
Yes.
Okay. Do you have an answer here?
No.
Okay. That's because ortho isomers, see, if you look at ortho substituted, so I have the electrophile here and the halogen here. This is ortho position to each other, right, Gaurav? They are very
Yes.
close together, and that's why they will have a lot of steric hindrance. And because of a lot of steric hindrance or steric repulsion, ortho isomers become the minor product produced in less quantity, and para isomers become the major product produced in more quantity. We've got this, Gaurav?
Okay. Yes.
Okay, and I hope you guys also got it. Now, and one more point which is important, which you have an entire paragraph in NCERT dedicated to this paragraph here. For me, it's example 10.9. Maybe you can see this when I upload the video. This is the paragraph there. If not, I'll talk about it in class anyway. But the point here is electrophilic substitution in haloarenes, it takes place slower as compared to benzene. Oh, you have that here as well in another part of the book. We'll talk about it. Uh, yeah, so electrophilic substitution in haloarenes, and you will see electrophilic substitution in only plain and simple benzene also, but in haloarenes, it's slower as compared to benzene. That's because haloarenes have a particular effect. There is a particular effect of halogens on the benzene, and that's negative inductive effect minus I effect. What is negative inductive effect? The halogens, they are electronegative compared to carbons of benzene. They pull up electrons to the electron density a little bit towards themselves, which is why they show a lesser tendency to undergo electrophilic substitution, but they still do undergo electrophilic substitution, which is why we'll see these classes of electrophilic substitution that we talked about: halogenation, nitration, sulfonation, and Friedel-Crafts alkylation and acylation. I want to talk about it in the class itself, but it seems like I have a bit of time, so I can talk about it now. How do you feel about that, Gaurav? There are just 4 or 5 reactions. Let me just talk about it anyway. Okay.
Okay, sounds good.
You feel up for it?
Yes.
Okay. So when we talk about halogenation, what is the reagent? The reagent here is we have to take halogen. So halogen, generally we write it as X2. Now that X2 could be, for the people, new people there, X2 could be F2 chlorine, Br2, oh sorry, Br2 or I2. Okay. Now, all of these, they are reagents, along with, plus you need something else. You need anhydrous, meaning without any water, FeCl3, or anhydrous AlCl3 could also work for this case. But yeah, we can take FeCl3, that would work better here. So what do you expect here the product to be formed for chlorobenzene with chlorine? If you're adding chlorine, as is done in this particular example, we are going to get this Cl stays here. Remember, electrophilic substitution, the original halogen is not disturbed whatsoever. The new thing gets added. So new chlorine has to go to 2 positions, one at ortho, and another position that it can go to is at para. Now, what do you think is the major product, Gaurav?
Second one.
The second one, the one that is at para position, this is our major product. The other is our minor product. Can we maybe, try to write the IUPAC name of these two molecules? Is it possible, Gaurav? Okay, I'll help you. Okay, this is 1, 2, and then 3, 4, 5, 6. This is how we number the benzene ring. So this is 1, comma 2, dichloro.
Dichlorobenzene,
Yes, dichlorobenzene. Now, if you look at the other one, how will we name this? 1, 2,
comma
3,
4.
4. Yes, 5, 6. This becomes 1, comma 4 dichlorobenzene. Okay.
Okay.
If you know the IUPAC names, guys, my squad, you can fast forward this, but I expect you to stick through the entirety of the video. Maybe I'll ask you a question at the end. Okay, now we'll move to the next reaction. Nitration. The reagent that we use is concentrated nitric acid, HNO3, plus concentrated sulfuric acid, H2SO4. Okay. And what do you get? You get a nitro substituted product. So here you have uh, chlorine at the position where it originally was. Now, Gaurav, do you have an idea of what we are going to get? This is simple.
Nitro group will attach.
Nitro group at ortho, and one
Para.
of the other product that you get will be nitro at para. Now, which is major? Like every other case, para is major, ortho one is minor. How do we name it? What's the IUPAC names of these two?
So what is the main functional group? I forgot. Is it
Okay,
chlorine or
so
nitro?
Hmm. Okay, we'll name this nitro as 1. You can do either way, but we'll name this nitro as 1, and then chlorine would be 2. You can number anti-clockwise also. It's not necessary that you number clockwise. You just have to follow the lowest locant rule. I hope you guys know.
Mhm.
So what do we call it? 2-chloro nitro benzene. Done?
Yeah.
So what's the major product then? Following the same set of rules, you have this as
4
4-chloronitrobenzene.
nitrogen.
Done?
Yes.
Okay. Any problem here?
No.
Okay. Or you can number nitro as 2 and chlorine as 1, and then we can switch places. It just has to be ortho with respect to another and para with respect to another. Now, if you look at the reagents for sulfonation, what is the reagent? There is just one single reagent for sulfonation, that is concentrated H2SO4, that will give you the sulfonated product. Okay. And okay, I think we are at the limit of time. What I want you to do, guys, just look at sulfonation, the products, major and minor product for sulfonation, and also look, if possible, look at Friedel-Crafts acylation and alkylation. There are two things, alkylation, acylation. I'll upload these on the drive as usual, and we can talk about this in class on Monday. And we have, what is it? Polyhalogen compounds, chloroform, and all of those to also talk about. And we'll be done with this chapter. I hope you watched this video in its entirety. If you did, I'll just give one question. So, which will follow SN2 faster? This is your question. There are, which follows SN2 faster? I'll give you two molecules. This is molecule 1. This is your first molecule, and um, okay, this is your second molecule. You need to answer which of these will react faster. I might ask you this question in your class itself, but remember, yeah, that sounds correct. Now, remember, you need to look at this question. This was, which was there here, this particular question. Let me make this even more clearer. I'll just put it up a little bit up. Yeah, this question, question number 19, this is a multiple correct answer type. I'll give you options in the group chat. Let me know which are the correct options here. All of you, I expect to answer this question. Okay, thank you, Gaurav, for uh, doing this with me. I'll just close the recording now.
Thank you.
Okay, I'll just give me 1 second.